All right, so now we're on to the data collection video for the LED experiment. And this is the lab that's taking the place of the self-design experiment. So I'm going to be a little less explicit about exactly what I want you to do for the analysis. I want to have you to have a little freedom to analyze it kind of in the best way you think works. So I'm going to talk through here the theory a little bit more so that that part is clear, and then we'll take a look at the information from the other two videos that you have at your disposal. So right now what we have on the screen is the equation for the energy of a photon. And the energy of a photon is Planck's constant times the frequency. Okay, so this is a pretty fundamental idea, an important idea. It's really the first idea of quantum physics, that light is a composition of, or light is composed of photons, and each of those photons has an amount of energy that's in proportion to its frequency. And that constant of proportionality is called Planck's constant. Your goal in this experiment is to determine Planck's constant. So if you could measure the energy of a photon and the frequency of a photon, then you could calculate what Planck's constant is. So how do we do that? Well, one thing that is a little bit helpful is translating between frequency and wavelength. So the speed of light we know, or we can take as a known quantity, 3 times 10 to the 8th meters per second. And so that gives us a way to translate between frequency and wavelength, because whatever the frequency is, if the speed of light is a known quantity, then we can calculate wavelength, and vice versa. So we can actually relate the energy to the wavelength, or relate the wavelength to the frequency, and then the frequency to the energy. All right. Now, the different colors have different wavelengths, and they come in a range. So what is blue light? Well, blue is sort of anywhere in this range. Green is anywhere in this range. Orange is anywhere in this range. Red is anywhere in this range. And it's somewhat subjective, but somewhat objective too, right? There are boundaries here. But we're dealing with, in this experiment, specific colored LEDs. And so we'd like to know specifically what wavelength they have, and then using this equation, we can calculate what, or at least as exact as possible, what frequency they have. So one part of this experiment is, what is the frequency of the LED that you're using? And we're doing that by figuring out their wavelength first and then calculating frequency. And the wavelengths are found from this experiment here with the spectrometer. So what I did in this experiment was shine the LEDs into the spectrometer. They went through this diffraction grating to spread out the light into its component wavelengths, and then you got a pattern. And that pattern, or those patterns, looked like this. Right? So we have blue, green, orange, red, and it's not very well defined. Okay, it's a little bit more narrow than maybe that table of information. So let's go back to the, see where were we? Let me put this one down. Okay, so let's look at blue. It's supposed to be between 430 and 500. That's technically blue light. Now, we have a slightly narrower range here, but you'll have to do two things. Estimate where the peak is, and you might just use these numbers here, but then also put an uncertainty amount on that, because it's not exactly 471 nanometers. There's a range. And so this range, where the peak is, tells you the information about the uncertainty in the wavelength, which will then translate into an uncertainty in the frequency, right? So this is the wavelength measurement You can use this as the best value of wavelength, but then you need to estimate the amount of uncertainty around that wavelength. And you could do that for each of these. And so some of them are a little bit more sharply defined than others. Apparently, the blue LED has a slightly broader spectrum than the orange, which looks like it has about the narrowest spectrum to it. Okay. So I'm not going to say too much about how you do those things. How do you figure out what the uncertainty is, or how would you estimate it, or how would you translate it into the frequency? So using this calculation. If you can't figure this out on your own and you need some help, I'm happy to explain it further. But I want you to let you do kind of as much as possible of this on your own, and try to figure things out, work through things as much as you can on your own. But if you do get stuck, definitely get in touch with me, and I will happily explain things in more detail. Okay, just to recap on this, our goal is to figure out what H is, and I've just talked about how you would get the frequency. So from the data that we collected in the first video, you have estimates for the wavelength with uncertainty, and then that should allow you to calculate the frequency with uncertainty. So we've got the right-hand side variable that we're measuring taken care of. Now on to the energy. Okay, so this is the key equation here, because the energy is, in this instance, coming from the electrical circuit. So it's coming from an electron. Okay, an electron is being excited, and as it's by the battery, and then it flows through the circuit, and that electron's energy becomes the energy of the photon. Well, how much energy did the electron have? Well, it had its charge times voltage. Remembering way back, one of the reasons I like this lab is it kind of puts together everything we've done all semester going back to the beginning. Very early on, we looked at spectral plots for sound waves. Now we just looked at spectrum plots for light waves. Then we talked about electricity and charge and electrostatics. We need to use that here also. The energy of the electron is charge times voltage. So it's accelerated through the voltage. Its energy becomes the energy of the light, becomes the energy of the photon. So left-hand side, energy of the electron, right-hand side, energy of the photon. We can take the charge of an electron as a known, just like we took the speed of light as a known quantity. And then what we're measuring essentially is the voltage. And you can multiply the charge times the voltage would be the energy that the photon has. The voltage comes from the second video. So let's bring that one up. Okay, so here's a screenshot from the voltage measurement video where we're looking at the orange LED. And so in the video, I'm tuning it back and forth just a little bit around where it starts to light up, and you're reading this number. Okay, again, you're going to have a measurement for the quantity, so in this case the voltage, and also an amount of uncertainty in that number. Now the uncertainty here is a little bit more complicated than a normal experiment. Normally you would be doing this in person, and you'd actually be looking at the LED with your own two eyes. Here you're limited a little bit by the screen, and I don't know exactly how this will look for you. I know how it looks for me. I'm able to see pretty well where the light turns on, and it looked to me like you can see the light turning on my screen where it was turning on in real life. So I'm a little bit confident that this is going to come out okay for everyone. But it's something to keep in the back of your mind if things don't look quite right on your screen. Hopefully you have access to some screen where you can make it big enough and clear enough to see where the light is. So if you're first trying this on your phone and it's hard to tell where the light turns on, then maybe you can get to a computer with a slightly bigger screen, better resolution. But it worked okay for me. So I checked this on my computer screen, it looked okay, and I checked it on my phone screen and it looked okay. When this light turns on, you'll want to record this number. Now, I would pick the value that corresponds with the, like this, you can see like a ring of light lighting on. So it lights up sort of in a little bit in stages. You might see a little flicker at the center and then the ring here. Just to make this a little bit more consistent, when you see a clear ring of light in the LED, use that value for the turn on point. Okay. Now you can record this to hundredths of a volt, but that won't be your uncertainty. You're not limited by your meter here. You're limited by your own eyes, your ability to detect where this turns on. So what you might do is try to pause the video a couple of different times and see what the meter says at each of those times, and then you can sort of get like a collection of data points and take the average and standard error, something like that, to do the uncertainty. Or maybe another way to approach it, it's equally valid, would be check the point where it looks like you can barely see any light on, and then go forward until it's definitely totally illuminated, and then you'll have a range in values for voltage, and you can use that to estimate your uncertainty in the value and just place your best measurement sort of in the middle of that range. So there's more than one way to do this. I'll let you decide what you think works best for you, given the setup that we have here. Okay, so let's go back to this. All right, so again, another recap. We're hoping to measure H. We get F from the wavelength. So we find wavelength with uncertainty. That will give us frequency with uncertainty. Then we're hoping to measure E, and that comes from this right here, the voltage, and we'll have that with uncertainty. So ultimately it's this equation, this whole equation that we're working with to calculate what H is. So the frequencies with uncertainty, the voltage with uncertainty, E you can treat as a known quantity and plug it in, and you can calculate H. There are a couple of different ways you can do this. You can take different values, make a table, average them out, get a value that way. You can make a graph. You can analyze it that way. How you choose to analyze the data set is really up to you. I want this to be your kind of analysis of the situation. At the end of the day, what you need to have is a value for H, an experimental value for H with uncertainty. So any way you can get there is good, and you can compare it to this number here. Note that this is an extremely small number, so the fact that you can get a value for this at all is pretty impressive. And the way you can measure something this small is by using something like light, which has such a small wavelength that you can probe that scale using the wavelength of light. And you should be able to get a number certainly within 10% error of this, but probably less. I think more like 4 or 5% error is reasonable. I might want to downgrade that a little bit given doing this across the video rather than in person. But if you get an answer that's like times 10 to the minus 37 or times 10 to the minus 31, then something has gone wrong, because you should be able to get it pretty close to the accepted value of Planck's constant. Okay, so I think I'll end it there. And as always, just let me know if you have questions.